Hello, everyone. Welcome to this presentation of findings surrounding the electric sea glider by Regent. On the next slide, we'll start by looking at the benefits of our topic. The sea glider is an all-electric aircraft. Therefore, it will eliminate greenhouse gas emissions from air and water travel. It will reduce travel times and costs, so airlines, ferry companies, and passengers will all benefit. And finally, for those of you watching, you will learn about science behind sustainable technologies that you can take with you going forward. So to begin, Jaden will talk about electric propulsion, which describes how the glider generates thrust and lift to move. Next, Thomas will talk about the battery and the process of optimizing the weight and power of the glider. Then Matthew, will talk about the control system, which explains how the glider flies safely close to the water. And then finally, Mitchell will talk about the hydrofoil hull design, which describes how the glider moves through air and water. So to begin, Jaden will talk about electric propulsion.
So, hi everyone, my name's Jaden and I'm going to be talking about electric propulsion. So you may be wondering how the glider actually flies without the use of any type of fuel. And in these days, you don't really see it commonly because it's mostly used in spacecrafts and satellites, but we're trying to make it more general to help the environment just a little bit. So the way electric propulsion works is it relies on a theory called Faraday's law. And Faraday's law works by taking electrical energy supplied by a battery or a battery bank and turning it into mechanical energy like a force or through the use of magnets. So in this figure here, we have this coil of wire. Then this magnet here is going to go inside of that coil of wire. And once it does, it's going to affect the magnetic field that's like inside of there. And it's going to change the current or the voltage that's passed through the circuit. So in the real world, how this is actually going to work on the glider is through electric induction motors. And these consist of two main sections. We have the stator, which is stationary, that's the stator, and the rotor, which moves around, which is the rotor. The rotor will rotate along its drive shaft here, and it has these small little magnets which are placed in at an angle to allow for rotation. The stator has a bunch of copper coil windings that when an electric current is passed into them, they are going to generate a magnetic field. You can see that in this figure here, as the blue lines there are going to represent the magnetic electric coils, and then these arrows here show the magnetic field inside. So when the rotor is placed inside of it, the magnets will cause it to spin. And this spinning is going to be transferred to a propeller from the drive shaft, and the propellers are going to cut through the air and cause the glider to move forwards. By tilting these propellers with a control system, you can cause lift as well. This is the basics behind how electric flight works, and next I'm going to be introducing Thomas to talk to you guys about the battery.
Hey guys, I'm Thomas and I'll be talking about the battery endurance. Next. Someone might ask, how are these electric planes powered? Are they like those remote-controlled planes? Surprisingly, it's actually very similar, but on a much larger scale. Unfortunately, we can't stuff any of these batteries seen here into the plane to make it work. They are much bigger. Next. The key differences in how an electric plane works and the normal airplane works is that fuel is needed to power the turbo engines, while an electric engine uses something else. Can we take a guess? That's right. It's electricity from a battery. Next. The redox reaction is the basis of how any battery works. If you paid attention in chemistry class, particles can share electrons, which charge each other. In a way, the redox reaction, a particle is oxidized, which means it gives an electron away, and a particle is reduced, which means it gains an electron. It is called reduced because its charge level is lowered by gaining this electron. In this picture, particle A shares its electron with particle B. It's very simple. Next. Now, a battery, how does it really work? There are four main components of a battery as seen here. The really important ones are the anode and the cathode. Remember particle A and particle B sharing electrons? Imagine that, but on a much larger scale within a battery. The act of sharing is truly wonderful, even to things that aren't even alive. By sharing, the flow of electrons from the anode to the cathode provide power to the frog, as we see in the picture. Next, batteries come in all shapes and sizes. However, airplane batteries come in more specific shapes and sizes. Battery cells are put into packs, and these packs are put into casings so they can easily be removed or added to an electric plane, such as these batteries here. A stack of batteries in a pack, which will be put into a case in an airplane. Next. Now, how long can the Regency glider last? Well, at full charge, when going at top speeds of 180 miles per hour, it can travel for 180 miles, lasting up to 1 hour for every charge of battery. This can easily get you from Ottawa to Montreal. Next, we move on to Matthew and his findings of the control systems.
Thanks, Thomas. Once again, I'm Matthew, and I'll talk about the control system. Now, many people, potentially some of you, have a fear of flying. And although the chances of getting in a plane crash are significantly lower than getting in a car crash, flying is still a much more common phobia. If the glider is to ever become a standard form of travel, people will need to have trust in it. This trust takes a long time to build, but one crash could be enough to discontinue it. With this in mind, the importance of the glider's control system cannot be stressed enough. For this section, my research question is, how does a glider fly safely at low altitudes? So if you look on the next slide, what this means is having our glider's altitude remain consistent here, here, and here to maintain a steady trajectory. Now, one way we can accomplish this is by using what's known as a proportional integral derivative controller. Now, these terms may seem unfamiliar to you, but what's important to remember is that the proportional component of the controller is accounting for our present error. The integral control is accounting for past error, and the derivative control is anticipating future error. And our error is simply what our desired altitude is minus our actual altitude. So if we go to the next slide, we can see this in action. Now the pilot of the glider inputs the altitude he wants to fly at. And that could be, let's say, 5 meters. And this is known as our set point, which I'll abbreviate using SP. Now the glider periodically measures its altitude. In a poorly controlled glider, it would look something like this if we plot it as a function of time. It would start down here, it would go up, it would overshoot, it would come back down, and then finally it would settle something like that. Now the proportional control is reducing this rise time, which is how long it takes to arrive near our set point. The integral control is eliminating this steady state error, which is a final difference between our set point and our process variable and our actual altitude. Finally, our derivative control is analyzing how fast the air is changing in order to prevent this overshoot. Over here, so we don't go too high, and over here, so we don't go too low and crash into the water. This is our process variable. Now, if you look on the next slide, combining all of these together will produce happy and safe passengers, and hopefully this will ease some of your fears of flying. Next, Mitchell will talk about the whole design of the glider and its hydrofoil, which talks about how the glider moves through air and water.
Thanks, Matthew. My name is Mitchell, and I investigated the hull design of the glider, particularly the hydrofoil. So here we have a photo of a guy riding on what appears to be like a multi-level surfboard thing. You're probably wondering how he's doing it. How is he doing this? Is it magic? No. The answer is a hydrofoil. Before I talk about hydrofoils, though, I'm going to talk a little bit about drag and the drag coefficient, which was my engineering theory, in order to understand why and how hydrofoils affect the glider and how the glider acts like both a boat and a plane. Next slide, please. Now, what is drag? It's defined as the force opposing an object's motion. And if you've ever biked into a headwind on a windy day, you'll know exactly what I'm talking about. Minimizing drag allows vehicles to be more efficient, travel longer, and travel faster. There are 4 factors affecting drag, shown on the next slide, which are cross-sectional area, which is the 2D area when you look at the front of the object, the density of the fluid surrounding the object, in this case, air or water, the speed that the vehicle is traveling, and the shape of the object when looked at from the side. The 3 main factors affecting the glider are the area, the density, and the shape, and these are best understood by comparing the difficulty of running in various situations. Objects with large frontal cross-sectional area, like a parachute, for example, are harder to move through space. This makes it harder and less efficient to run with. Next is density. If I asked you to run through water or run through air, which would you pick? Probably air. And that's because water is more than 830 times denser than air, meaning it requires a lot more work to move through. So keep this in mind for the glider. The glider speed is fixed by how fast the engines can spin, so it's not as significant as the other 3 factors. And the final one is the shape of the object, and this is also visualized by running with a parachute, but instead when looking at it from the side. So something like this half sphere here. This half sphere has a drag coefficient that's really high, 0.42, meaning it's inefficient and produces a lot of drag, which makes it harder to run with. Now all these principles of a person running act the same way on the glider. So in the next slide, you can see that the hull of the glider is really streamlined and has a small frontal area. And this helps to reduce the drag coefficient. But the key elements are these 2 hydrofoils here on the V, and then there's another small one on the back. And the image on the next slide helps demonstrate how hydrofoils work. So it's kind of hard to tell, but if you picture 2 particles here traveling, the first one traveling over the wing and the other one traveling under, this line is slightly on the top, is slightly longer. And so they have to both reach the end at the same point in time, which means this particle has to travel slightly faster than on the bottom. And this leads to a lower pressure just because of fluid properties. So this lower pressure causes the wing to want to rise up into that low pressure region. And so this is demonstrated when I'm blowing this piece of paper on the top side of it. You can see that the paper wants to rise to this low pressure because of the fast flowing air on the top. So yeah, you can try this at home if you have a piece of paper. It's a pretty cool experiment and kind of not what you would expect to happen. But so this principle is exactly how the glider's hydrofoils manipulate the water to produce a lifting force. Now, as the glider speeds up, the hydrofoils generate more and more lift, and the more lift produced, the more the glider rises out of the water. And the more the glider rises out of the water, the easier it becomes to travel because of the less dense air. And so this is the key to the glider's success and the reason it can be so efficient. So in summary, the glider's minimal cross-sectional area, streamlined body, and hydrofoils all play key roles in allowing it to function like both a boat and a plane. So those are our 4 topics. We hope you found our presentation on the electric propulsion system, the electric battery, navigation system, and the hull design of the Regen Sea glider interesting and informative. The glider has the potential to completely revolutionize coastal travel by lowering travel times and costs, and could be a large step forward in the fight